very accurate design of constant beam width beamformers. Okay. By the way, sometimes we just want that the beam width will be constant in frequency. Sometimes we want that the position of the nulls, the position of the nulls or the side lobes will also be independent of frequency. So we call it different, we have different names. If the beam pattern doesn't change in frequency, we call it frequency invariant beam pattern. If only the beam width remains the same, is independent of frequency, but the side lobes may change for different frequencies, we call it constant beam width beamformer. Okay? It depends what we like. So when I said that for high frequencies we don't want to distort the signal like a low-pass filter, it's enough that the beam width will be constant. So you don't want to add more constraints if they are not necessary. But if it's important to keep the null, for example, you know that the null for certain frequency, for a certain direction, it depends on the frequency. So suppose that there is a source that comes from a certain direction and you want to put null. This is called also null beamforming. And you want that it will remain in the same direction for all frequencies. And maybe you don't know, but you want to keep the side lobes the same, independent of frequency. So it's possible to design, when I said design beamformer, it means how to design these weights. So it's possible to design it such that the beam pattern will be frequency invariant. But of course, you add more constraints. If it's not unnecessary, then don't do that, because it limits the performance. You know, in mathematics and optimization, when you have constraints, you pay for that. You pay for that with the performance. So the more constraints that you have, it lowers the performance because you have the constraints. Or you need to pay with that with additional hardware, additional software. When you have more constraints, you pay for that. Performance, hardware, software, whatever, complexity, and so on. So try to take the minimal constraints that you actually need, always with optimization. Maximum directivity beamformer. So I talked about when you want to maximize the directivity, this is the directivity of the beamformer. So this is the expression that we got for far field. If it's near field, of course, we need to change in the numerator the beam pattern for the near field source. Okay, so this is, we will talk about it maybe later. So how do we maximize this? What do we mean? We maximize. We need to choose the weights, the beamformer, such that this ratio, this is the array gain for diffuse noise, which is the directivity factor, will be maximum. How do we do that? So when you want to maximize something, the first thing in mathematics, optimization, is to write it as a function of what? Of the parameters. So we need to write this, array gain, this directivity factor, as a function of the weights. How do we do that? So we can write the directivity pattern as a function of the weights. How do we do that? You see, the directivity pattern is written like this for far field source. And far field, and when you see it here, what does it mean? If I write it like this is the phase differences between sensors. So it means that we used uniform linear array. Okay? But actually, I can get something similar for any configuration of the array, but for simplicity, we use here uniform linear array with the inter-element spacing, which is D. So we can write this like this. W transform conjugate multiplied with D. So in a vector form, it looks like this. So this summation, in a vector form, it looks like this. So we can write the directivity factor as a function of the directivity pattern using the weight vector that we multiply each tensor. So we have a weight vector. And also the integral, we can take it out, and the integral over this vector. If I go back, you see, this vector is called the propagation vector or the steering vector. Actually, what does it contain? It contains this value, the phases that come or measured that are obtained with each tensor. So the integral here, it doesn't depend on the weights because we took the weights out of the integral. It's not dependent on the weights is what we want to find. It's independent of the direction, but D depends on the direction. So we can compute this integral in advance. And now we can write it like this. By the way, we can compute this integral, you see, which is for diffuse noise. So we can call it, this is a matrix. We can call this matrix, we can write it as gamma, okay? And actually we know exactly how to find this gamma. So we have this ratio, you see? So this was the first stage. We want that the directivity which we want to maximize, we wrote it as a function of W and other things which are independent of W. But we know them. This is the steering vector or propagation vector for the desired direction. And this is gamma, which we know how to compute. So how do we maximize this? So we can, of course, maximize this. Is it sufficient? What does it mean that we maximize this? It means, by the way, I didn't write here the dependence on the frequency. We maximize this, we maximize W, we maximize the directivity by using W for each frequency. Okay, so this ratio depends on the frequency. Okay, but I didn't write it for simplicity of notation. Okay, so this directivity, you see that the numerator is the gain for the desired source, and the denominator, what is the gain for what? Diffuse noise. And we want to maximize this ratio for each frequency. We can do it independently for each frequency. Now, suppose that this ratio is high for a certain frequency. Is it sufficient? So it maximizes the directivity for that frequency. But also what we want, very important, that the gain, the numerator, will be independent of frequency. Why? Because if it depends on the frequency, it means that we have different gains for the desired source for different frequencies. So this is a distortion. It's like distorting the desired source. So what we need to maximize WH for frequency, okay, over WF, D, F, and it depends on the desired source direction. Okay? Say like this. Divided by WH F gamma F W. Okay? But we also need to put a certain constraint that the desired source gain will be independent of frequency. So it's subject to WHF dF phi fs theta fs this any constant, if it equals to any constant which is independent of frequency, it's fine. I don't care about the constant. So I can write it as constant equals to 1 because it's independent. I don't care if this constant will be 2, 3, whatever. This is just a gain for the desired source. But it's important that this constant will be independent of the frequency. Okay, so you see it here. You see it here. So if it's 1, so the numerator is 1, so I need to minimize the denominator. I need to minimize the denominator subject to the same constraint. It's the same. See? So this is the problem of finding the maximum directivity beamformer. So we can solve this. How do we solve this? You see, this is a vector. I need to find this vector, which minimizes this. And by the way, you can put here any matrix Q. If Q is the cross spectral density of the noise, so it actually will maximize this ratio, this array gain, for any type of noise. For any type of noise that is characterized with this cross spectral matrix Q. If I put here gamma, it will maximize the directivity. Okay? So suppose that I know, what does it mean here? It's the cross spectral matrix Q for any noise. So if suppose that I know exactly the noise, I can measure it. And I can measure the correlation between noise signals in different sensors. So I suppose that I can find this matrix for a specific noise. And I maximize this. So this is called minimum variance distortionless response. Minimum variance distortionless response. This is the distortionless response because it doesn't distort the desired source. So this is the constraint of the distortionless response. And minimum variance, it means that it minimizes the gain for the noise. So it minimizes the denominator, minimizes the gain, the average gain for the noise, and we have distortionless response. So this numerator is constant, independent of frequency. So this problem, the solution to this problem is called minimum variance distortionless response beamformer. And if instead of Q we put gamma, what we had before, gamma, which is suitable, it's the same matrix, but it's suitable for diffuse noise, then how do we call it? Instead of minimum variance distortionless response, it will be called maximum directivity beamformer. Okay? So the solution for this problem, the weight, you see this is the solution, Q minus 1, D, DH. So D is what we have here. This is D. For the direction, this is the propagation vector or steering vector for the direction of the desired source. and Q, we assume that we measure it or we estimate it. This is the solution. Note that the numerator is a vector. The denominator, what is it? A scalar, yes, because you see dH, Q minus 1, Q is a matrix, D is a column vector. So this is a scalar, it's just a scalar. How do we obtain it? So I give you some exercise, okay? The exercise prove that the solution to this problem using Lagrange multiplier, okay? Prove that this is the solution. Obtain this solution. By the way, if I substitute this into the constraint, okay, WHD. So I get 1, okay? WHD is the same like DHW. DHW equals to 1. So I actually, this solution satisfies the constraint. If I put here DH, actually it's 1. But also you need to show that it minimizes. So don't just use it. Prove that you can obtain this expression for the MVDR. And one of the problems of MVDR and also maximum directivity factor is that the white noise gain, when we try to maximize the directivity or we find the maximum minimum variance distortionless response, we get very low white noise gain, which means that the gain for white noise, you see here, if the gain for white noise, if we put here in this matrix, we put the identity matrix. See, instead of Q or gamma, the gain, the white noise gain, okay, of the array, it will be WHD magnitude squared divided by WHW. So we put here identity matrix. So this is the array gain for spatially white noise, for thermal noise. And as I said, we don't want that this will be too low for any frequency. So we need to limit that this will be larger than a certain threshold. So this is the minimum acceptable threshold. If it's, for example, minus 20 dB, it means that we allow this threshold, we allow that the beamformer will amplify the thermal noise by 20 dB. So it means that the sensors, the thermal noise in the sensors is not too high. Okay? So it's not enough to formulate a problem like this, maximum directivity or minimum variance distortionless response beamformer. Usually, in practical cases, you need to add another constraint. So this will be the additional constraint, that the white noise gain is larger than a certain threshold. Sometimes this threshold, maybe it's independent of the frequency. Sometimes maybe you want to depend it on the frequency, but usually maybe you can put here a threshold that is independent on the frequency. It means how much thermal noise you can allow to amplify at the output of the beamformer. So what will be the solution if I add this additional constraint? It will be like this. So I can add several, instead of just one constraint here, I can add several constraints. So this is called linear constraints. For example, you see what I write here, that I want constant gain for a certain direction. Maybe I have other directions that I want to keep nulls in that direction. So maybe I have other constraint, for example, WHF, DF for certain other direction, maybe phi1, theta 1. Maybe I want to put here 0 or any other value, 0.1 or something like that. But if I have a few constraints, I can put these constraints, I can write it like this. I can write it like this. So I can write the linear constraints so instead of this constraint, D, I can write it as DH F theta 0 phi 0 DH F theta 1 phi 1. So this is different directions and so on until we have a few theta P phi P. So suppose that I have, you see each vector here now is a row vector. So this is a matrix. And this matrix, we call it CH. Okay? And if we multiply it with the vector W, we get certain values. So for this, the first value, it will be 1. The other directions, maybe we put zeros. Maybe we want, maybe we know that for other directions we have interferences. So we will put zeros in the other directions. So suppose that we want to solve to minimize this denominator subject to this constraint, the linear constraint. So this is the solution, and we can put epsilon, some epsilon here, which is larger than 0, such that it will also satisfy the constraint and the white noise gain. So the white noise gain will be higher than a certain threshold. So this solution is called robust LCMV, linearly constrained minimum variance beamformer. Okay, why is it called, why does it, we call it robust? Because we also have a constraint and the white noise gain. So how do we change it to near field? What do you think? How do we change it to near field? Everything that we saw here. So we saw a few things. We saw MVDR. Minimum variance distortionless response beamformer. MVDR beamformer. We saw it. We saw maximum directivity factor. Max directivity factor beamformer. We saw LCMV, linearly constrained minimum variance with the matrix C. So if we have more than one constraint and one direction, if we have additional linear constraints using this matrix of constraint, we call it linearly constrained minimum variance beamformer. And for all this, and actually we have more beamformers, for all this, we can add an additional constraint that the white noise gain will be higher than a certain threshold. If we add constraint that the white noise gain will be higher than a certain threshold, so all this will be robust. So we call robust MVDR, robust max ADF, robust LCMV. Okay? Understand that? We have additional beamformers. And now, if we change this, instead of far field to near field, what do we need to change? Okay, so let's go for the MVDR. What do we need to change? Only this. So the propagation vector, or the steering vector, which you call it here, we need to change it to near field. So the constraint that it's equal to 1, it will be with D that is near field. If we go to max DF, so instead of the matrix Q, it will be with the matrix gamma, which is relevant to diffuse noise that comes from all directions. So it will be robust, and we can add this constraint. So it will be robust max DF for near field source. If we have LCMV, so we take this matrix. Do we need to take everything here, near field or far field? So it depends. It depends on the sources. Okay? So maybe if it will be for near field, we need to put here R0, here R1, RP. Okay? So it depends. If the source here, the desired source is in the near field, so it will be near field. If this source, we don't care about the distance because it's far field, so it will be far field, and so on. Okay, so we understand this. We understand how to define the problem of finding the optimal beamformer, and then we need to solve it. And the solution is quite simple. It's quite straightforward. What we showed before, you can also prove it. Any questions? So these are the modifications for near field sources. Okay. We assume when you put constraints like this, you assume that you know the directions if it's in the far field. But if you assume that the source is in the near field, you need to know not only the direction, but you need to know the position, which means the distance and direction. If you don't know, which is a good question, if I don't know. So one of the ways is to put a constraint not at a certain point in space, but on a region around it. Okay? So this is called region of interest beamforming. And if I have nulls in certain region, I can call it region of non-interest beamforming. Okay? So I can solve it instead for a certain position of the source, for certain regions, certain area of source, desired source or indesired or non-interest sources where I want to put nulls. I'll give you an example. Okay? So suppose that there are two loudspeakers here with music. I play one music, one song, maybe classical music, and one loudspeaker. And I put another loudspeaker here. I play rock songs, different type of music. So I put headphones on my ear, and I sit over there. Somebody else sits over there. And maybe we want to listen to different sources. I want to listen only to the classical music. And maybe somebody that sits here wants only to listen to the pop music. How do we do that? So I want, and I don't know exactly the position. So it's a region. So I want to maximize the signal that I received from the desired source, desired loudspeaker, without any distortion. Okay? So I want to constrain that it will, with no distortion, I will get only the source from one loudspeaker, and the other loudspeaker, it will be suppressed as much as possible. It will be minimum. Okay, the power will be minimum. And then I can listen only to one source. And vice versa. So it depends on where is this. So I need to design it. Okay? I want to show you something. Where is it? Like this? Just a minute. Okay, just a minute. Let me see here. Okay. Okay.
So you're wearing headphones?
Just a minute. Maybe I increase the volume. So I show you, maybe turn off the light here, here, or maybe here. Oh, oh no, sorry. Okay, good. Yeah, this is good. Thank you.
Create a sound bubble. When the sound bubble is on, then sounds outside of the bubble will disappear so that you can hear my voice very clearly. If you were at a restaurant, then you can use a sound bubble to focus on the speakers at your table while everybody else outside of your bubble will be silenced.
So this example shows that somebody wears headphones like this, and he wants to talk to somebody and listen only to people inside the bubble. So they call it bubble sound. So he wants to listen only to sources inside the bubble, and people that speak outside or any sources outside the bubble will be suppressed.
It uses AI on the device to process audio from 6 microphones around the headband. And if someone walks into your bubble,
and you can hear them. You can hear them both, actually.
Because we're both inside of the sound bubble.
And the sound bubble silences all the speakers outside of it.
We're evaluating the system. The system picks up the speakers that are nearby the user, and it will silence the people who are outside. If the system is working, then you should only be able to hear my voice, and you should be able to hear me clearly. We're evaluating the system. The system picks up the speakers that are nearby the user, and it will silence the people who are outside. If the system is working, then you should only be able to hear my voice, and you should be able to hear me clearly.
Okay, so you see a nice example of sound bubble and how to design it. We will talk about that. Okay. So we talked about this. Okay, so you see it's the same, you just need to change, you understand it. Okay, so we can skip that. I told you, generalized silo canceller or adaptive beamformer. We will talk about it when we talk about adaptive beamforming. Now I want to continue with single channel signal enhancement in the time domain. So we finished the overview of the objective. Now that you understand, so we can continue with more details. So single channel signal enhancement, it means that we have single source, single sensor, that the single sensor we have, in the single sensor, we have the desired source and undesired. So I will talk about what is the signal model and problem formulation, what linear filtering, performance measures, and optimal filters. Okay, after we have the overview, I think things can be much more quick to define this. You will see that for single sensor, perhaps you already know some of the material, so I will go, it's more like definition. So when we move to multiple sensors, we understand the definitions and how to do that. Okay, so suppose that with a single sensor, this is a single sensor, this is the measured signal. And suppose that we have two components. One is desired, one is undesired. And using this measurement, we want to estimate the desired signal. By the way, here, T is discrete. It's not continuous. Okay? So we have sampled signal. And we want to estimate a sample of the desired source. If I ask you something like that, you will not be able to estimate because you need more information. You need some information in order to estimate xt out of this measurement. So the question is, what type of information do I need? If I use only one sample of y, and I want to separate into two components, that is desired sample plus undesired sample, I don't think I can do that. I need to provide more information. So with linear filters, what we have is something like that. So instead of one sample, we can take a vector of samples. Maybe it's possible to turn on the light. So I can ask, okay, I want to obtain an estimate of xt. Let's call it zt. This is an estimate of xt. And a linear estimator, it means that I will use some samples of the measurement and I will multiply them with a filter. So it will be like this. Summation from I equals to 1 to L, or let's say even from 0 to L minus 1. And then I take samples. Suppose that I want causal estimator. So it means that I take the samples from T minus I, like this. So I have the recent L samples of the measurements. I will multiply them with HI, like this. So it's a superposition, a linear superposition of the recent L samples of the measurements. And the question is, how do I design these linear weights in order to estimate the sample at time t of the desired signal? So this is a linear filter. Of course, we can do it with nonlinear filters as well, but let's limit for simplicity our expressions to linear filters. Okay, so what do we do? We take L samples, L recent samples of the measurements. It's a vector y. And we want to use this vector in order to find these optimal weights. When we want to define optimal weight, we need to define what is the optimality criterion, which is important, and what is the information that we need in order to separate between the desired source, the desired signal x, and the undesired interferences, which are included in the vector, or in the signal v. Okay, so the minimal information that we need is a correlation. What does it mean, correlation? So this is a correlation matrix. Okay. You see, I take the correlation for the vector y. So I know how any two samples in these vectors, how do they correlate? correlate is correlation is on the average. Okay, so we have the expectation of y transpose. It's transpose because we deal with real signals. And it equals to the correlation because we assume that the desired signal X and the undesired interference V are uncorrelated. So the correlation matrix of the desired signal equals to the correlation of this is the measurement, the correlation matrix of the measurement. It's a summation of the correlation matrix for the desired signal and the correlation matrix for the interference, for the noise. And we assume that the rank of the correlation matrix for the noise is full rank, and the correlation for the desired signal is lower rank, maybe less than full rank. We will talk about it. Why do we need to do that? Okay? Because if this matrix is lower rank, it means that the desired signal is within a certain signal subspace. We will talk what is a signal subspace. So if the rank is lower here, it means that we can represent any signal in a smaller signal subspace, so we can remove or suppress anything outside this subspace. So we can suppress more noise. And we will talk about definitions and what does it mean. Okay, so linear filtering, it means that the output sample, the estimate after the estimation, is a superposition of the L samples from the measurements. So we can write it as H transpose in a vector form, H transpose Y, where H contains the weights that we give to each sample. So this is called linear filtering for estimation. By the way, if we use future samples of Y, here we use only past samples of Y in the past. So we have the current, and total we use L samples of the measurement. If we use future samples of Y, how do we call it? So instead of causal estimation, how do we call it? How do we, if we use future samples of Y, what? Non-causal. So it's non-causal estimation. If we don't use the current sample of Y, suppose that we don't have YT. We have only L samples, but in the past, without the sample at time T. How do we call it? Instead of estimation? Prediction. Exactly. Why? Because we don't have the measurement at time T. We want to estimate XT based on previous, only past samples, without the current sample. So we call it prediction. Okay? So we have different names, but and if the function is linear, so we call it linear. Linear filtering, linear prediction, and so on. If the function is any nonlinear function of the measurement, we call it nonlinear filtering, estimation, prediction. For example, if we use neural network to find the output, the estimator, based on some samples, and neural network is nonlinear, so we have nonlinear estimation, prediction, causal, non-causal, whatever, all these names. Okay? But here we focus on linear because it's simpler for the definitions and for understanding and for the intuition. Okay, so the block diagram looks like that. We have desired signal vector, L samples, noise. So we have here L samples of the measurement. We multiply it with certain weights vector, and we get an estimate of the sample xt. These are vectors. All these are vectors. This is a scalar. Only one sample. Okay, so we can write the output. This is the output as H transpose X plus V. So it has two components because it's a linear filter. So this is the advantage, that we can define things more easily. So we have this sample contains two components. One component is the filter desired component, and this is the residual noise, which is H transpose V. So ideally, we want to have the filter desired equal to the sample, the original signal of the clean signal. So ideally, what we want to have is H transpose XT equals, or we want it to be as close as possible to XT. Okay? This is what we want to have. Because this, what does it mean if it equals? It means that we have perfect estimate. No distortion. Perfect estimate. And also, perfect estimation, it's not enough. Because we can take Y, if we take H, equals to 1, 0, 0. Do we obtain here equality? Yes, because we just take the first sample and the component here. So we have undistorted signal that is estimated. But we will have all the noise in the original signal. It's like we didn't do anything. With this filter, we didn't do anything. We just take the measurements as is without reducing the noise. So we want also the residual noise to go to 0 as much as possible. So we want to estimate the signal without distortion and suppress the noise. But of course, this is a trade-off. We cannot do both. So we can measure what is the variance of this, of the filter desired, and what is the variance of the residual noise. We want that the variance of this, or the error, to be as small as possible, and the residual noise to be as low as possible. So the variance of the estimate contains two components, the variance of the filter desired and the variance of the residual noise. From this, we can compute also the signal to noise ratio. So the variance of the filter desired is H transpose RXH, and the variance of the residual noise is H transpose RVH. Rx and RV are the correlation matrices of the desired and the noise. Okay? How do we get it? Very easily, you see? Because expectation of Z squared, we said that Z squared, Z is a scalar, which equals to H transpose Y. So we can write it like this, or we can write it Y transpose H. Okay? The same. Because here, so we can write expectation, the variance of Z, the variance of Z, we can write it as E. Now, it's better to write Z multiplied with Z, but differently. H transpose Y, Y transpose H. Okay? Even though we can write this as squared, but it's better to write it like this. Because like this, we can write it as H transpose Ry H. And Ry, because X and V are independent, so we can write it like this. Two components. You see, with linear filtering, everything is much simpler. So we can define the input signal to noise ratio. Input signal to noise ratio is actually, what does it mean? In the original signal. In the original signal, we have y t equals to xt plus vt. So the input SNR is the ratio between the variance of x and the variance of v. This is the input SNR. And of course, we can write it as trace of Rx divided by trace of Rv. It's the same. Okay? What is the output SNR? So the output SNR is the variance. We said that Z, okay, Zt, which is the estimate of xt, is X filter desired plus V residual noise. So the output SNR is the ratio of the variance of X filter desired by the variance of the residual noise. So it's H transpose Rxh divided by H transpose Rvh. This is the output SNR. And what is the gain in signal to noise ratio after filtering? The gain in SNR is the ratio between output SNR divided by input SNR. Okay? So for example, I can ask you how to find H, how to find this vector such that the output SNR will be maximum, or the gain in SNR. You see, the input SNR is independent of H, is the input. But after the linear filter, the estimator, I can ask you, how do I find H such that the output SNR, or the gain in SNR, same, will be maximum? Which filter, which filter maximizes the gain in SNR? How do I define it? So which H maximizes this ratio? Okay? So it's possible to solve it. Actually, it's not difficult. It's also possible to prove it. But there is a way to maximize this ratio. Okay? But I want to ask you, before we solve it, I will show you how to solve it. We'll talk about it. But it's more important to know what type of information do I use. What is the information do I use to solve this problem? Assume that I have Rx and Rv, right? Because once I have Rx and Rv, I can find the filter that maximizes the output SNR. What is the information contained in Rx and Rv? Okay? Think about it. I have one sensor. I have these measurements, sample after sample. I sample this single channel measurements. So I have, what does it mean that I have Rx? It means that any two samples, such that any two samples that are distanced by the time less than L samples, okay? So if I take two samples from the vector X, you know, the vector L, the vector X contains the vector X contains the signals xt, xt minus 1, and so on, until x t minus L plus 1. So it contains the L recent samples of X. So if you take any two samples from this vector, I know their correlation, which is a lot of information. And I know this also for the noise vector. So I know RV. So I know Rx and I know RV. And based on that, I can find H that maximizes the output SNR. But this, in practice, is very difficult to know. Okay? So here, I assume that I know it. If I know it, I can find the filter that maximizes the SNR. But this, we will see some examples. It's a lot of information, and it's very difficult to know that. After we define the performance measures, we will find optimal filters that optimize things. Okay? So this is the identity filter. Just like I mentioned. If I have 1 and the rest is 0, if I take H equal to that, what happens? I don't do anything. So the output SNR will be the same as the input SNR, because I didn't change anything. I keep the original measurement as is. Do I have distortion in the measurements? No distortion. But I didn't do anything for the noise. I didn't reduce any noise. So the output SNR remains as the input SNR. Noise reduction factor. What does it mean, noise reduction factor? How much noise I have at the output compared to the input. So this is the ratio between the variance at the input, variance of the noise at the input, and variance at the noise at the output, at Z. So this ratio, we want it to be as high as possible or as low as possible. We want it to be high or low? High, exactly. High, it means that we reduced a lot of noise. The denominator, we want it to be as small as possible. It's the variance of the residual noise. We want this ratio to be very high. We can define also something similar, but instead of noise reduction factor, we can define desired signal reduction factor, which means what is the variance of the desired source at the input divided by the variance of the desired source at the output. So ideally, we want this to be ratio equal to 1, because we don't want to distort or to change or to reduce the desired. We want this to be closer as much as possible to 1. And then we think that there is no reduction of the desired source. And we have certain relations between the gain in SNR and the noise reduction and desired signal reduction factor. Okay, so it's very easy to show this ratio. We can also define distortion index, the desired signal distortion index. What does it mean? You see, the output of the filter contains 2 components. So we can ask, what is the error, the expectation of the error, between the filter desired and the original signal? So here we don't take into account the residual noise. We just care about the distortion, and it's normalized. So we have this expression. Okay, so from here we can move to here, and many times, okay, so we want that this distortion index, which is roughly between 0 and 1, it's normalized. We want to be as close as possible to 0. So we want to find H such that this expression is as close as possible to 0, which means that the signal is less distorted. Mean squared error, it means what is the error between the estimate of X and X. So it takes into account two components. One is the distortion, and one is the residual noise. So we want to minimize both components. One component is the distortion, which is related to the signal, and one is the residual noise. So the mean squared error takes into account both components. The mean squared error related to the distortion and mean squared error related to the residual noise. And we can say that we want to minimize both. Okay, and of course we have some relations between the ratio. So the ratio between the mean squared error related to the distortion and the residual noise, we have some relations between the performance measures, like this. Okay, so it's easy to show. And before we move on,